Welcome to Moon Whisper Sleep, a quiet corner where curiosity can soften and science gently walks you toward rest. Tonight, we're traveling somewhere almost no one will ever visit in person, yet nearly everyone has heard about in documentaries, books, or passing mentions. It's not a distant moon or a faraway planet. It's right here on Earth, a place so dark, so deep, and so strange that for most of human history, it existed only in stories and imagination. The Mariana Trench, the deepest abyss on our planet. Before we slowly sink into that darkness together, let me ask you something. From where in the world are you listening tonight? Are you near the coast, where waves breathe in and out against the shore? Or are you in a city far inland, where the ocean is only a distant idea? Something you've seen on screens more often than in real life? Maybe you've stood on a beach, watching the waves crash again and again, and wondered, how far does this water go? How deep is deep? What lives in the places no light reaches? Or maybe the ocean, for you, is just a picture, blue on a map, a moving background behind movie characters, a word more than a place. Either way, right now, with nothing but your thoughts and this gentle story, you and I are going to travel into a part of the ocean that almost no one has seen with their own eyes. If slow journeys like this, calm, curious, and a little sleepy, bring you comfort, I'd be grateful if you liked or subscribed. It helps this quiet space find others who might need a soft landing at the end of the day, or a calm companion in the middle of the night. Thank you for being here. Thank you for bringing your curiosity. Now, let's begin to leave the surface behind. Imagine you're standing at the edge of the sea. The horizon stretches out in a gentle line. Maybe there are a few ships in the distance, or seabirds circling above. The surface looks simple, just water, wind, and light. But beneath those waves lies an entire world, layered like pages in a book. Picture yourself slipping into the water and beginning to swim downward. First, everything feels familiar. Sunlight pours through the surface in bright beams. You can see silver fish weaving around you, and reefs glowing in reds, oranges, and purples. This is the sunlit zone, the part of the ocean most people imagine when they think of underwater. Keep going, and the light begins to dim. Colors fade to blues and grays. Details soften. Shapes blur. You cross into the twilight zone, where the last traces of sunlight weaken and stretch. Eventually, you reach a point where the sun disappears entirely. Now, there is no natural light at all. This is the beginning of the true abyss, where the ocean becomes a midnight world. If you keep sinking far, far beyond scuba divers, beyond most submarines, beyond the reach of ordinary exploration, you eventually arrive at something even more extreme. A long, curved tear in the ocean floor, a wound in the Earth's crust, deeper than Mount Everest is tall. The Mariana Trench. It lies in the western Pacific Ocean, east of the Philippines and south of Japan, curving like a great scar across the seabed. It stretches for over 1,500 miles, roughly the distance from Los Angeles to Kansas City. But what captures the imagination isn't how long it is, but how deep. At its deepest point, Challenger Deep, the trench plunges nearly 11 kilometers below sea level, about 36,000 feet. If you picked up Mount Everest and placed it upside down into the trench, its summit would still be covered by more than a mile of water. Pause for a moment and let that sink in. A mountain higher than any on Earth, hidden completely beneath the ocean, with water still to spare above it. Down there, the pressure is more than 1,000 times greater than the air pressing on you right now at the surface. It's a force that can crush metal, collapse submarines, and compress air into something more like a solid than a gas. And yet, somehow, life still exists there. We'll return to that miracle later. For now, let's drift backward in time and remember that for most of human history, the ocean itself was mystery enough, even without knowing that such an abyss existed. For ancient sailors, there was no sonar, no satellites, no deep-sea submersibles. The sea was already terrifying and vast, filled with storms, strange currents, and dangers they couldn't predict. They had no idea that a trench deeper than any mountain is tall lay hidden beneath the Pacific. Instead of maps filled with detailed depth lines and numbers, they had stories. They spoke of giant serpents dragging ships into the depths, of whirlpools swallowing entire fleets, of gods and spirits ruling the waters below. On early maps, the edges of the known world often carried little drawings of sea monsters and dragons, with phrases like "Here be dragons" written in blank ocean spaces. It wasn't that cartographers believed in literal dragons. It was their way of saying, "Here our knowledge ends. Beyond this point, anything could be true." To many cultures, the sea wasn't just a body of water. It was a presence, a moody being that could be calm and gentle one day and violent the next. The Polynesians saw it as a pathway of stars and waves, guiding their canoes across thousands of miles. In the north, people imagined giants and gods dwelling in stormy seas. The Greeks told stories of Poseidon, ruler of earthquakes and oceans. Underneath all these myths was a simple fact. No one knew what lay below. Even relatively shallow waters were hard to measure. Sailors used ropes with heavy weights, often lead or cannonballs, tied to the end. They would lower the line over the side of the ship and wait, hoping to feel the moment it touched bottom. This method, called sounding, worked near the coast but became nearly useless in the open ocean. Currents tugged the rope sideways. The weight snagged on rocks or simply never seemed to land. The deeper the water, the less reliable every reading became. Imagine standing on the deck of a wooden ship, watching coil after coil of rope slip through your hands into the darkness for hours, not knowing if it would ever reach the seabed. For centuries, that was as close as humans could get to exploring the abyss. The ocean floor might as well have been another planet. No one had seen it. No one knew its shape. Many believed the sea might be bottomless or uniform, deep, but not unimaginably deep. And silently, in a remote part of the Pacific, the Mariana Trench waited in the dark, utterly unknown. As time passed, and ships explored more of the world, curiosity grew. In the 16th and 17th centuries, as European powers mapped coastlines and crossed new oceans, a quiet question began to form. We know what's across the sea, but what exactly is beneath it? By the 19th century, that question turned practical. Engineers wanted to lay telegraph cables across the ocean floor to connect continents. To do that, they needed to know the depth and shape of the seabed. A broken cable at extreme depths meant broken communication. So measuring the ocean stopped being just a matter of curiosity. It became infrastructure. Expeditions were launched with longer cables, better weights, and systematic recording. One of the most important of these was the voyage of HMS Challenger in the 1870s. This ship traveled nearly 70,000 nautical miles, lowering weighted lines and collecting samples from the deep sea. Slowly, a picture began to form. The sea floor wasn't flat. It had ridges, plains, and canyons. Among these measurements was one particularly deep reading in the Western Pacific, over 8,000 meters. No one knew it yet, but they had brushed the edge of the deepest trench on Earth. Even so, rope-based methods had limits. Ropes stretched, currents pulled, weights detached. A depth of 8,000 meters might really be 7,800 or 8,200. The numbers were amazing, but imprecise. The abyss remained hazy, just out of clear focus. It wasn't until the 20th century, with the rise of sonar, that the ocean truly began to give up its secrets. During World War I, navies needed a way to detect submarines. The solution was sound. By sending sound pulses into the water and timing how long they took to echo back, they could estimate distance, first to submarines and later to the seafloor itself. The principle was simple. Sound travels through water at a known speed. Measure how long it takes for a ping to return, divide by 2, and you know how far away the reflecting surface is. Now, instead of lowering ropes for hours, ships could map depth in seconds. Throughout the 1920s and 1930s, survey vessels crisscrossed the Pacific with echo sounders, sending countless pings down into the darkness. Each ping returned a number. Those numbers, plotted together, revealed something astonishing. The ocean floor was as dramatic and varied as the continents, full of mountains, ridges, and trenches. Again and again, in one particular area east of the Mariana Islands, readings showed depths that seemed almost unbelievable. At first, some scientists suspected errors, but as more measurements arrived from different ships, a clear pattern emerged. There was a gigantic trench out there, long, curved, and unimaginably deep. By the mid-20th century, the Mariana Trench was firmly established as the deepest known feature on Earth. Challenger Deep, its lowest point, later confirmed by more precise surveys, marked the very bottom of our planet's oceanic envelope. For geologists, this trench was a key piece of evidence for plate tectonics, a place where one plate of the Earth's crust is being pushed beneath another in a process called subduction. For biologists, it became a natural laboratory, a question wrapped in darkness. Can life exist under such extreme pressure, cold, and isolation? For everyone else, it was something more emotional. Proof that even here on Earth, there are places as strange and remote as alien worlds. Understand numbers alone, though, can be hard to feel. 11 kilometers, 36,000 feet, more than 1,000 atmospheres of pressure. Our minds aren't built to intuitively grasp scales like that. So, scientists and storytellers use comparisons to pull those extremes into our everyday world. Imagine Mount Everest, the tallest mountain above sea level, flipped upside down and gently lowered into the ocean. Its peak would still be more than a mile beneath the surface. The highest point on Earth would vanish, and the ocean would look unchanged. Imagine a passenger jet cruising at 35,000 feet. From that height, the world seems impossibly far below. Clouds become blankets. Cities become patchwork. Now invert the scene. Instead of being above the clouds, imagine that same height but under the ocean. That's the rough depth of the trench. Or think of the tallest building in the world, the Burj Khalifa in Dubai. You could stack over a dozen of them on top of each other inside the trench and still not break the surface. Even these comparisons only get us partway there. The trench is not just deep in a physical sense, it's deep in time as well. If you dropped a weighted object that sank at 2 meters per second, faster than most real objects, it would still take roughly an hour and a half to reach the bottom. 90 minutes of falling through darkness. During that time, the ship above would drift, the world would move, and still the weight would be descending. And then there's the pressure. At the surface, you live comfortably under 1 atmosphere of pressure, the weight of all the air above you. It's about 14 pounds per square inch, and your body quietly balances it from within. Dive 10 meters into the ocean, and you add another atmosphere. At 30 or 40 meters, divers need training and specialized gear. At 100 meters, almost no one goes without advanced equipment. At the bottom of the Mariana Trench, the pressure is more than 1,000 atmospheres. It's like having dozens of fully loaded airplanes stacked on top of you. Ordinary submarines would be crushed. Steel bends, glass shatters. Anything that visits the abyss must be designed with extraordinary care. Spherical pressure hulls, thick metal walls, carefully engineered joints. And even then, explorers hear the hull creak and groan as it descends, reminding them of just how thin the line between safety and catastrophe is. Yet, in this crushing weight, life has found a way. The life in the trench doesn't survive in spite of the pressure. It survives with it, shaped by it. Many deep-sea creatures have soft, flexible bodies rather than hard shells that might crack. Their cell membranes contain special molecules that keep them stable when squeezed. Their proteins are adapted to function under conditions that would destroy ours. Some of these organisms can't survive in shallower water. For them, the lower pressure world near the surface is as hostile and unnatural as the abyss is to us. The trench becomes more than a place. It becomes a hint, a clue that life can exist in environments we once thought impossible. If organisms can thrive under 1,000 atmospheres of pressure in eternal darkness, perhaps something similar could exist in the hidden oceans beneath the ice of Europa or Enceladus, moons of Jupiter and Saturn. The abyss, in that sense, is not just Earth's deepest point. It's also a model, a quiet argument that says, don't be too quick to assume where life can or cannot exist. One more thing makes the trench uniquely otherworldly: the darkness. Long before you reach the abyss, sunlight disappears. At a few hundred meters down, you enter the twilight zone. Dim, blue, and fading. Go deeper still, and all trace of sunlight vanishes. The water becomes a realm of permanent night. Human eyes are not designed for such darkness. We're rarely in true blackness on land. There's always some glow from the moon, from distant cities, from screens, from stars. But in the deep ocean, there is no sky, no moonlight, no starlight, just black water stretching in all directions. And remarkably, that's where light begins again, this time from life itself. Many deep-sea creatures produce their own light through bioluminescence. Tiny chemical reactions inside their bodies create glows of blue, green, or red. Some flash to attract prey. Some pulse to communicate. Some glow to camouflage themselves or to confuse predators. It's as if the ocean has its own private constellations, not pinned to the ceiling of the sky, but scattered through the water in moving, flickering patterns. Other creatures abandon light altogether. They lose their eyes over evolutionary time, relying instead on vibrations, chemical cues, or pressure changes to sense their surroundings. In a world where sight fails, other senses rise to take its place. For humans, these conditions are so different from our daily experience that they feel almost unreal. To explore this world, we must bring our own light, on cameras, on submersibles, knowing that every beam we shine is a small, temporary intrusion into a darkness that has existed for millions of years. So as you lie here listening, imagine yourself slowly drifting down. The surface far above, sparkling and loud. The light dimming, colors fading. Fish and corals are giving way to strange, pale creatures. Then only darkness, pressure, and quiet. Somewhere below, the ocean floor falls away into a trench deeper than Everest is tall. The pressure climbs, the temperature falls, and the water becomes still and heavy. Most of us will never see it. Most of us will only ever know it as a number, a diagram, a single dark line on a map. But tonight, gently, calmly, without strain, you've already started to visit it in your mind. Because the Mariana Trench is not only a place of rock and water. It's also a reminder that even on a planet we think we know, there are still edges of the map. Still blank spaces. Still mysteries waiting patiently in the dark. And as we continue this journey, we'll move from the history of how we discovered this abyss into the stories of what we found there. The machines that dared to dive, the animals that call it home, and what this deep, silent scar on the earth might tell us about life beyond our world. For now, just let the surface slip a little farther away, and let the thought of that distant, quiet trench rock you gently towards sleep. Powerful beams from a submersible can carve a brief bubble of visibility in the water, but beyond that small halo, the darkness of the trench returns almost immediately. In photographs and films, the light from those lamps fades into black only a few meters away, as if the ocean is swallowing it. What we see in those images is not how the trench normally looks, but a tiny stage briefly illuminated inside a vast, unseen world. Turn the lights off, and the environment disappears completely. Explorers inside submersibles often report seeing nothing but their own reflections in the viewport unless the lamps are on. The sensation is disorienting and reminds us that the abyss is not designed for human senses. Down here, the usual rhythm of day and night no longer exists. On the surface, life follows the cycle of sunlight. Plants open and close, predators hunt at specific hours, and bodies prepare to sleep when darkness approaches. But in the deepest ocean, there is no sunrise and no sunset. Time is not marked by light, but by other patterns. The slow drift of particles falling from the surface, occasional pulses of nutrients, or internal biological clocks tuned to something we barely understand. The familiar pattern of morning, noon, and night, the pattern that shapes our own lives, simply does not apply. Most of the Earth is like this. We think of our planet as bright and sunlit, with blue skies and green landscapes. In reality, more than 70% of Earth is covered by ocean, and most of that ocean is in permanent darkness. The surface layer, the one that sunlight reaches, is just a thin, glowing film on top of an immense shadowed volume. The Mariana Trench is simply the deepest part of this shadowed world, the farthest point from the sun that life on Earth can reach. When scientists first sent cameras and instruments into the deepest parts of the ocean, they expected to find an almost lifeless desert. The conditions seemed too extreme: cold, crushing pressure, and complete absence of light. Instead, they discovered communities of organisms perfectly adapted to those extremes. Amphipods, small, shrimp-like scavengers, move across the seabed in swarms. Ghostly snailfish glide close to the bottom, their bodies soft and pale. Bacteria and other microbes thrive inside the sediments, not using sunlight at all, but feeding on chemicals and slow-falling organic matter from above. What looks harsh to us is normal to them. Eternal night is not an obstacle but a background condition of life. For humans, the darkness invites imagination. For centuries, people filled the unseen ocean with stories. Monsters, spirits, and unknown powers. Today, myths have given way to measurements and video, but the feeling of mystery remains. We still cannot see very far. Our instruments reveal only a narrow cone of light or a thin band of data in a vast, invisible volume. The trench reminds us that most of our planet is hidden from direct view, and that our knowledge is still a small island in a much larger sea. If light cannot reach these depths, sound can. The deep ocean is not silent. It is one of the most acoustically active environments on Earth. Unlike light, which fades rapidly in water, sound travels faster and much farther. This is why whales can communicate over great distances and why navies use sonar to detect objects many kilometers away. In certain layers of the ocean, known as deep sound channels, sound can be trapped and guided across entire ocean basins. In the region of the Mariana Trench, pressure and temperature combine to bend and focus sound. When scientists lowered hydrophones, underwater microphones, into these depths, they did not record emptiness. They heard a complex soundscape. There was the low rumble of distant earthquakes and the muffled echoes of underwater landslides. Storms at the surface sent their signatures downward. Rain striking the sea as a faint hiss, waves and thunder as long rolling booms. Even far-away events, thousands of kilometers distant, could be detected as subtle vibrations. There were biological sounds as well. Some deep-sea animals communicate or hunt using sound. Snapping crustaceans, fish that vibrate their swim bladders, and other creatures producing clicks, pulses, or short calls. For animals living in darkness, sound is as important as sight is for us. It reveals movement, distance, and the presence of other organisms. To a hydrophone lowered into the trench, the deep ocean becomes a kind of global listening point. It records earthquakes near one continent, storms above another, and whale calls from far away, all layered together. Mixed in with these natural signals are human noises. Ship engines, propellers, and sonar pulses contribute to the acoustic environment even at great depth. The trench, remote as it is, still carries the traces of our activity. Some recordings include sounds that are not immediately identifiable. Tonal sweeps, mysterious groans, or rising and falling notes. Over time, several of these have been traced to icebergs, unfamiliar whale calls, or geological events. Others remain unexplained, reminders that the deep ocean still holds phenomena we have not fully classified. In a submersible, the human ear hears very little of this directly. The hull insulates against most external sound. Instead, explorers notice the creaks and groans of the vessel itself as it adjusts to changing pressure. Instruments do the listening. Through them, Scientists can hear the activity of the planet transmitted through water, storms, quakes, and living things, converging even at the bottom of the trench. Seen this way, the abyss is not isolated. It is connected to the entire ocean through sound. If the soundscape is surprising, the appearance of the creatures living here is even more so. Without sunlight, color has a very different meaning. There is no need for green leaves or brightly patterned feathers. Many deep-sea animals are transparent, their tissues almost invisible in the dark. Others are milky white or faintly pink because pigment offers no advantage when there is no ambient light. And then there are those that make their own light. Bioluminescence is one of the defining traits of life in the deep sea. Many organisms, bacteria, jellyfish, fish, squid, carry chemical systems that can produce light on demand. They flash, glow, or shimmer in blues and greens, sometimes in reds. These lights are used for many purposes. Some species lure prey using a glowing lure, like anglerfish, whose illuminated appendage draws small animals close enough to be swallowed. Others use light for camouflage, emitting a faint glow from their undersides to blend with the tiny amount of light filtering down from above, a strategy called counter-illumination. Still others use light as a form of communication, signaling to potential mates or warning rivals with specific patterns of flashes. Many creatures of the abyss have shapes that seem almost unreal. Giant squid and other large cephalopods have enormous eyes to collect the faintest possible glimmers of light. Deep-sea eels have expandable jaws and stomachs, allowing them to swallow prey nearly as large as themselves. Some animals appear ugly or distorted when brought to the surface because their bodies are adapted to a very different pressure regime. Once removed from that pressure, their normal shape collapses. Blobfish are perhaps the most famous example. In their natural environment, they are neutrally buoyant, not sagging like the caricatures we often see in photographs taken at the surface. Size also behaves differently in the deep sea. Certain groups show deep-sea gigantism, where related species grow much larger at depth than their shallow water relatives. Giant isopods, for example, resemble oversized pill bugs and live on the seafloor at great depths. The reasons for this pattern are not fully understood. Low temperatures, slow metabolisms, and the need to travel long distances to find food may all play roles. At smaller scales, microbial life flourishes in the sediments of the trench. These microbes do not rely on sunlight. Many use chemosynthesis, drawing energy from chemical compounds such as methane, hydrogen, or sulfides. Some are extremophiles, organisms that not only tolerate but require high pressure and low temperature. They help cycle nutrients and support higher levels of the food web. Their existence shows that life can be powered by chemistry alone, without direct input from the sun. This has important implications for the search for life beyond Earth. If microbes can thrive in dark, pressurized oceans on Earth, they might also exist in subsurface oceans on icy moons like Europa or Enceladus. Food in the trench is scarce and arrives slowly. Most of the energy that supports its ecosystems comes from above in the form of marine snow, fine particles of organic material that fall continuously from the sunlit layers of the ocean. These particles include dead plankton, fragments of larger organisms, bits of fecal matter, and other debris. The descent can take weeks. By the time they reach the bottom, much of the easily used energy has already been consumed by organisms higher in the water column. Despite this, life on the seafloor has adapted to make use of every fragment. Microbes break down the organic matter in the sediment. Small scavengers pick through the mud. When a large carcass, such as a dead whale or large fish, sinks all the way to the bottom, it becomes a temporary oasis. Animals converge from the surrounding darkness to feed. Over time, bacteria, worms, crustaceans, and fish strip the carcass of tissue, then colonize the bones themselves. Nothing is wasted. The trench's ecosystem is slow but efficient. In the mud, microbial cells can number in the millions per cubic centimeter. Amphipods swarm around bait placed by researchers, revealing that even in the most remote basin, life is ready to respond when energy appears. Some fish species are found only at these depths, adapted so completely to high pressure that they cannot survive in shallower water. The abundance here is not obvious at first glance. There are no dense forests or coral reefs, but at the scale of microorganisms and small animals, the seafloor is busier than it looks. For us, these forms of life expand the definition of what normal biology is. We tend to think of forests, grasslands, and shallow oceans as the standard habitats of Earth, but in terms of sheer volume, cold, dark water dominates. The inhabitants of the trench do not see themselves as strange. They are well adapted to their environment. It is our own dependence on air, warmth, and light that makes us the unusual ones in the context of the planet as a whole. Once scientists realized how diverse and resilient deep-sea life is, a natural question followed. Could humans ever visit these depths directly and observe them with their own eyes? For decades, the answer appeared to be no. The pressure at nearly 11 kilometers down is more than 1,000 times greater than at the surface. Any vessel traveling there must withstand forces that would crush ordinary submarines. The first successful human descent to the Challenger Deep came in 1960, when the bathyscaphe Trieste reached the bottom of the trench. Designed by Auguste Piccard and acquired by the U.S. Navy, the Trieste was an unusual craft. A large float filled with gasoline for buoyancy and a heavy steel sphere slung beneath it for the crew. The sphere's steel walls were more than 12 centimeters thick, and inside there was room for only 2 people. On January 23, 1960, Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed into this small sphere near Guam. The hatch was sealed, and the Trieste began its descent, weighted by tons of iron ballast. As it sank, daylight faded to blue, then to black. Outside, pressure climbed steadily. Inside, the 2 men listened to the creaks of the hull and monitored their instruments. At one point, at around 9,000 meters, an outer observation window cracked under the stress. The inner layers held, but the incident underlined how thin the margin of safety was. After nearly 5 hours of descent, the depth gauge indicated about 10,900 meters. The Trieste had reached the Challenger Deep. Through the small portholes and under the glow of the external lights, they saw a flat seafloor covered in fine sediment. They reported observing small organisms moving along the bottom, a sign that complex life could survive even at that extreme pressure. They remained there for about 20 minutes, then released ballast and began their ascent. After roughly 9 hours underwater, they returned to the surface. Their dive demonstrated that human beings, enclosed in carefully engineered vessels, could visit the deepest point in the ocean. For more than 50 years, no other manned dive reached that depth again. The trench was studied by unmanned probes and sonar surveys, but no person looked out a window from the bottom. During that time, space exploration advanced dramatically. Humans walked on the moon, spacecraft flew by outer planets, and telescopes looked deep into the universe. Meanwhile, the deepest part of our own planet remained almost untouched. In 2012, filmmaker and explorer James Cameron completed a solo dive to the Challenger Deep in a custom-built submersible named Deep Sea Challenger. Unlike the Trieste, this vehicle was tall and narrow, designed to descend rapidly and be piloted by a single person. Its buoyancy came from advanced syntactic foam capable of withstanding extreme pressure. Cameron sat inside a small spherical pressure hull, surrounded by controls, cameras, and instruments. His descent took a few hours. As he went deeper, communication with the surface became limited to brief acoustic messages. Outside, the ocean grew darker and colder. Bioluminescent organisms occasionally flashed past the viewport. Eventually, the submersible reached the seafloor at nearly 10,900 meters. Cameron spent several hours there, longer than any previous human visit, filming, collecting samples, and observing. The scene that his lights revealed was much like the one described in 1960. A relatively flat, muddy plain with sediments slowly drifting down and small creatures moving in and out of view. Samples returned from that dive contained microbes with remarkable adaptations to high pressure. The video footage provided clear images of the bottom to scientists and the public. Cameron's dive showed that modern technology could make such expeditions more frequent, though they remain technically demanding and expensive. Today, most exploration of the Mariana Trench is carried out by robotic and autonomous vehicles. These instruments can remain at depth for longer periods, carry specialized sensors, and conduct surveys without the risks associated with placing humans in such hostile conditions. They map the seafloor with high-resolution sonar, measure temperature and chemistry, and capture images and samples from areas humans have never seen directly. Even with these advances, only a tiny fraction of the trench has been observed in detail. The Challenger Deep is not a single point but a small region with several basins of similar depth. Measurements of its maximum depth vary slightly, usually between about 10,900 and 11,000 meters, depending on method and conditions. The exact number is still refined as instruments improve. In some ways, that lingering uncertainty is fitting. It reminds us that the trench resists complete definition, holding back a small part of its truth. What we do know is already extraordinary. The Mariana Trench and the Challenger Deep are places where the Earth's crust bends and sinks back into the mantle, where pressure reaches extreme levels, where light never penetrates, and where life persists using strategies unfamiliar to life on land. Sound, not sight, connects these depths to the rest of the planet. Chemistry, not sunlight, fuels many of its microbes. For the few who have descended there, and for the many who study it from afar, the trench is a frontier that reveals how much of our own world still lies beyond direct human experience. As you picture this environment, the darkness, the pressure, the distant echoes carried by water, the slow rain of particles, the quiet movements of pale animals on the seafloor, you might notice how far it is from everyday life, yet how close it is in physical distance. It lies beneath the same sky, under the same ocean that touches familiar shores. The abyss is not on another planet. It is part of our own. It simply exists at a depth where human senses and bodies cannot function without help. Knowing that such a place exists, hidden under the waves, can change how we think about Earth. We often look up when we think of mystery toward stars and galaxies. The Mariana Trench reminds us to look down as well, to remember that beneath the calm surface of the sea lies a world as strange and demanding as any we might imagine elsewhere in the cosmos. A world of darkness, pressure, sound, and quiet, yet persistent life. Exploring the deepest parts of the ocean has never been an easy task. While human-occupied submersibles created some of history's most iconic moments, the truth is that most of what we know about the Mariana Trench comes from machines, robots built to go where humans cannot. These vehicles do not need air to breathe, light to see, or space to stretch. They do not feel fear, fatigue, or isolation. Their metal hulls can be engineered to resist the crushing weight of nearly 11 kilometers of water. And so, while human dives are rare and symbolic, robotic dives are steady and continuous. They are the quiet, tireless explorers of the deep. Robotic systems come in several forms. Free-falling landers are simple frames weighted enough to sink to the bottom, carrying cameras, sensors, and sometimes bait to attract life. Tethered remotely operated vehicles, ROVs, are controlled from a ship above through long cables that transmit power and commands. And then there are autonomous vehicles, free-swimming robots that follow programmed missions and make decisions without human input. Japan's Keiko was among the first to repeatedly reach the Challenger Deep in the 1990s, capturing images of amphipods and collecting sediment samples. Later, the United States developed Nereus, a hybrid ROV/AUV capable of reaching the deepest seafloor. In 2009, Nereus touched the Challenger Deep before being lost to pressure 5 years later, a reminder of the enormous forces these machines confront. Despite these risks, robots have a clear advantage. They can remain at depth far longer than any human-occupied submersible. What human divers achieve in hours, robots can extend into days. They can be deployed repeatedly, gathering continuous footage and building datasets that reveal the trench in unprecedented detail. The images they return are haunting in their beauty. Vast plains of fine sediment, currents swirling faint clouds of particles, trails left by slow-moving creatures, and sudden swarms of amphipods drawn to bait. Cameras have recorded pale snailfish drifting gracefully, gelatinous bodies perfectly adapted to pressures that would crush most forms of life. Other dives have revealed unusual jelly-like forms and delicate transparent organisms drifting through the dark. Robots also collect samples, sediment, water, small creatures, captured in sealed containers that close under pressure. These samples are later studied in laboratories, where scientists uncover the biochemical tricks that allow trench life to survive. Some bacteria metabolize chemicals in ways not seen anywhere else, thriving under pressures that would destroy ordinary cells. Their adaptations have implications for biotechnology, medicine, and astrobiology. And robots have helped decode the geology of the trench. They have mapped the seafloor with sonar, traced fault lines, documented landslides triggered by earthquakes, and monitored seismic activity. Every measurement adds another layer to our understanding of the Earth's interior. For the engineers and pilots controlling these machines, the experience is strangely surreal. Instead of peering through a porthole, they sit in dim control rooms on the surface. They watch screens showing the view from robotic eyes, guide mechanical arms with joysticks, and monitor data flowing in real time. The descent into darkness is experienced at a distance, but the tension remains. Each mission carries the risk of losing a vehicle forever. Despite decades of exploration, the Mariana Trench remains largely unknown. Robots illuminate only small patches of the abyss at a time. What lies hidden between those glimpses is still one of Earth's great mysteries. Yet with each dive, the picture grows clearer. Life where none was expected, geology more dynamic than once believed, and ecosystems shaped by chemistry rather than sunlight. To understand the trench, we must understand the forces that created it. The Earth's crust is divided into tectonic plates, giant slabs that float on the partially molten mantle. They move only centimeters per year, but over millions of years their collisions and separations reshape the entire planet. Where plates collide, they form boundaries. Some rise into mountains, others slide past each other, and in rare cases, one plate dives beneath another. This process, subduction, is what created the Mariana Trench. Here, the vast Pacific Plate bends downward beneath the smaller Mariana Plate. As the plate sinks, it drags the seafloor into a deep arc. The Mariana Trench is the most extreme expression of this process. A profound scar where Earth's crust dives toward the mantle. Above the trench, the Mariana Islands rise from volcanic activity triggered by subduction. As the descending plate heats and releases water into the mantle above, the melting point drops, producing magma. This magma rises through the crust to form volcanoes. Without subduction, the islands would not exist. Earthquakes are common along the trench. As plates grind past one another, stress builds until it releases in sudden jolts. Many quakes are small, detectable only by instruments, but others can shake the islands and produce tsunamis. The trench is not an isolated geological feature. It is a living boundary where the planet continually reshapes itself. Sediments accumulating at the bottom of the trench preserve chemical records of Earth's past climate. By drilling cores and analyzing layers, scientists reconstruct the temperature of ancient oceans, atmospheric conditions, and glacial cycles. The trench is a library of Earth's memory. Minerals under extreme pressure transform into forms not found elsewhere. These high-pressure minerals help scientists understand the conditions deep within Earth's mantle. Robotic explorers have documented underwater landslides, chemical plumes venting from the seafloor, and seismic vibrations traveling through the crust. The trench reminds us that geology operates on timescales far beyond human lifetimes. Plates continue to move. The trench deepens, shifts, and evolves. Volcanoes rise and fall. Earthquakes rumble. Human history is a flicker in comparison. At the bottom of the trench, pressure exceeds 1,000 times that at the surface. The temperature hovers near freezing, and sunlight never arrives. Food is scarce, delivered only by the slow rain of organic debris falling from above. And yet, life thrives. The smallest life, bacteria, play the largest role. The sediments are filled with microbial communities that feed on chemicals seeping from rocks or drifting down from the surface. Many use chemosynthesis, converting hydrogen, methane, or sulfur into energy. For them, chemistry replaces sunlight. These bacteria are extremophiles, adapted to pressures that would crush most cells. Their proteins are specially structured for stability. Their membranes contain unique molecules that prevent collapse. Some produce enzymes that function only at depth, enzymes that fall apart near the surface. They reveal just how flexible life can be when pushed to extremes. Amphipods, transparent, shrimp-like crustaceans, appear in dense swarms around baited traps. Some species contain chemical pollutants identical to those produced by human industry, a sign that even the deepest ocean is not isolated from the surface world. The snailfish, pale and gelatinous, is perhaps the most iconic trench vertebrate. With soft bodies and delicate bones, they would collapse if brought to shallower waters. But here, in crushing pressure, they glide effortlessly. They are the deepest known fish on Earth. Food scarcity shapes every adaptation. Marine snow, tiny particles of organic matter, falls slowly to the seafloor. Most of it is consumed long before reaching the bottom, yet the trickle sustains an entire ecosystem. Occasionally, a large carcass sinks, delivering a feast that draws scavengers for miles. A remarkable molecule, TMAO, trimethylamine N-oxide, helps stabilize proteins under pressure. The deeper the fish, the more TMAO their tissues contain. It is a chemical shield, a molecular armor that allows life to function where it should not. Life here is built on chemistry, not sunlight. Chemosynthetic bacteria form the base of the food web. Larger creatures eat bacteria or each other, creating an ecosystem disconnected from the sun. These systems resemble what scientists expect on other worlds. Oceans beneath the icy crusts of Europa or Enceladus, where chemical energy, not sunlight, sustains life. Studying these organisms broadens the definition of habitability. The trench teaches us that life can arise in extreme darkness, pressure, and cold. It forces us to reconsider what other planets might harbor life. For decades, scientists believed the deep trench was too remote to be affected by human activity. But the first robotic footage revealed a sobering truth. Even here, pollution has arrived. A plastic bag was found lying in the mud of the Challenger Deep. Microplastics are now embedded in sediment samples. Amphipods contain synthetic pollutants such as PCBs, chemicals once used in industry and banned for their toxicity. These pollutants have traveled thousands of kilometers and thousands of meters downward. Pollution at such depth demonstrates how interconnected the ocean truly is. What enters at the surface eventually sinks. Plastics endure for centuries. Chemical contaminants accumulate in animals at the very edge of life. The trench has become not only a natural archive but also a repository for human waste. And yet, life persists. Amphipods continue to thrive. Bacteria continue to metabolize. But survival does not equal safety. These impacts may alter growth, reproduction, or metabolism in ways we do not yet understand. The Mariana Trench offers a glimpse into environments that may exist beyond Earth. The possibility of life in the subsurface oceans of Europa or Enceladus grows more compelling when we see organisms thriving without sunlight, relying only on chemical energy. Europa's deep ocean, sealed beneath ice, may host microbial life similar to trench bacteria. Enceladus's plumes, rich in salts and organic molecules, resemble the chemical environments near Earth's hydrothermal vents. If life exists there, it may resemble the trench's extremophiles, adapted to pressure, darkness, and chemical cycles. Studying the trench helps astrobiologists refine the search for extraterrestrial life. Every snailfish swimming in the dark, every extremophile bacterium thriving in toxic mud, offers a hint of what life on other worlds might look like. The parallels extend to engineering. Deep-sea submersibles and spacecraft share challenges. Extreme pressure or vacuum, darkness, and the need to protect delicate instruments. Both descend into the unknown, carrying human curiosity to places we cannot physically go. The abyss and space are opposites, yet they evoke the same sensations. Isolation, perspective, awe. The next era of trench exploration will rely heavily on robots. Fleets of autonomous systems may one day map the trench continuously, patrolling its slopes like deep-sea satellites. New sensors will measure chemistry with greater precision. DNA sequencing may occur directly on the seafloor, identifying species without bringing them to the surface. International collaboration may create networks of seafloor observatories that monitor seismic activity, chemical fluxes, and microbial communities over decades. Human dives will remain rare but meaningful. New submersibles may offer panoramic windows, better safety, and longer bottom times. These missions will continue to inspire imagination and public fascination. At the same time, the question of deep-sea mining looms. Metals such as cobalt and nickel lie on the seafloor, tempting industry. But trench ecosystems are fragile and slow to recover. The debate between exploitation and preservation will shape the future of the deepest ocean. Virtual reality, documentaries, and public outreach will connect more people to this remote world. The trench may become as familiar to the public as space, even as it remains profoundly mysterious. No matter how much we learn, the Mariana Trench retains its sense of silence, darkness, and depth. It is a place beyond ordinary human experience, a reminder that most of our planet remains unseen. Life in the trench is resilient yet delicate, extraordinary yet vulnerable. It teaches us about adaptation, persistence, and the creativity of biology under pressure. It also reflects our impact. Plastic fragments and chemical residues lying beside amphipods and snailfish remind us that even the deepest places bear traces of our presence. And it connects us to the cosmos. If life can thrive here, perhaps it can thrive elsewhere. The abyss becomes a mirror, reflecting the possibilities of life in the universe. As you imagine the descent, light fading, water darkening, pressure rising, you can picture a quiet plain at the bottom of the world, drifting particles, faint glows, and timeless stillness. A place where life continues, unseen, unchanged by whether we are watching. The Mariana Trench is not an end, but a beginning, an invitation to wonder, to learn, and to explore. As our journey through the deepest places of Earth gently comes to an end, let your mind settle, like the quiet sediment drifting to the seafloor. You've traveled through darkness, pressure, and silence. And yet, in all of it, there was life. Life is adapting, surviving, and transforming in ways almost impossible to imagine. And just like the creatures of the trench, you too are allowed to rest, to float, to let go of everything that feels heavy. Here, in this quiet moment, there is nothing you need to solve and nowhere you need to be. Just breathe slowly as the ocean breathes around you. If your eyes grow heavy, let them close gently. If sleep begins to rise like a slow, warm tide, allow it to carry you wherever it wishes. And when you return, whether tomorrow or on another quiet night, Moon Whisper Sleep will be here, ready to take you on another calm and curious journey. For now, rest deeply, sleep peacefully, and may your dreams be as soft and boundless as the deepest waters of our planet. Good night, explorer.